Unit 9b deals with electric field and electric potential. The electric field is a force field that emanates from a charged particle. This electric field will exert a force on any other charged object that enters the electric field. So we have an equation right here relating the electric force to the electric field and the charge of some test charge. This means that the electric field will have units of newtons per coulomb. And the electric field points away from positive charges and into negative charges. We'll take a look at that again in the next slide as well, but there is a direction to it. Electric field is a vector. And similar to what we talked about last time, we use a capital Q to indicate the point charge that generates the electric field, and we use lowercase q to indicate the test charge that feels a force from the electric field. This test charge will always be positive, so we always want to think about where a positive charge would go or what force it would feel based on the electric field that it's in. We can use electric field lines to represent the electric field around a charged object. So we can see the direction of the field for positive charges points away from the positive charge, and we can see for negative charges that the electric field points into the negative charge. And when you're drawing these electric field lines, you just need to draw an arrow either going into or away from the negative or positive charge respectively. And the more arrows that you draw, that means that the electric field is stronger. It has a higher value. So the closer together that these lines are drawn, that means that the electric field is stronger. Since electric field is a vector, we will need to follow vector rules, vector math rules. So if we have an electric field that is pointing only in the vertical direction and an electric field that is pointing only in the horizontal direction, we can use vector addition to add those up and figure out what their resultant vector will be for the electric field. Also, you might need to use trigonometry to think about angles and different components to some two-dimensional vector. So we can draw electric field lines for a single point charge, either a positive or negative charge, but we can also draw electric field lines for a combination of charges, like this one right here where we have two negative charges near each other. The electric field lines need to go into a negative charge, but we see that both of these electric fields in the middle are competing with each other. They're counteracting each other. There would be an electric field pulling into this charge on the left, and there would be an electric field pulling into the charge on the right. One of those is pulling left, one of those is pulling right, and so those two will cancel out because they are vectors. So there's effectively no electric field between these two negative charges. However, if we think about a dipole, that would be a set of charges where we have a positive and a negative near each other. The electric field lines leave the positive charge going away from it and enter the negative charge going toward it. So the strongest electric field will be right between the two charges because that's where the electric field lines are the most tightly packed together. Since an electric field exerts a force on charged particles, if we exert that force over a distance, we will do some work on the charged particle. And this means that we will impart some energy onto the charged particle. And this is a special kind of energy. We call this electric energy. And this is the energy required to move a charge through an electric field. You want to be really careful not to mix up EE, the electric energy, with the vector E, the electric field. These are two different quantities. This is a capital E with an arrow above it. That's the electric field. And this is a capital E with a subscript E and no vector arrow. That's because this is a scalar. This is the electric energy. So a charged particle moving through an electric field is very similar to a ball with mass rolling down a hill. As the charged particle moves through that electric field, it will give up some energy, just like this ball rolling down the hill gives up some gravitational energy. The electric potential describes the amount of energy in a system per unit charge. So we have an equation for the potential which says V equals the electric energy divided by charge, and sometimes this V will just be called the potential, but it is not the potential energy and it is not quite exactly the voltage either. The voltage is actually a difference in the electric potential. So if we think about this electric potential as being related to a ball rolling down a hill, the electric potential, V, is like the height of this hill. And as we go down in potential, as we go down in height, we lose some energy. Similarly, the potential difference involves the amount of energy that changes per unit charge. Or in other words, you can think of this as the steepness of your electrical hill that the positive charge is rolling down. We can rearrange this equation to solve for the electric energy, and we see that the electric energy is equal to the charge times the voltage. And so, if we do coulombs times volts, we actually get a unit for a joule. And if we specifically plug in the charge of an electron for Q, the elementary charge value, we can come up with this new unit for energy called an electron volt. So that is just a different unit for energy. It's not the standard, but it is equal to some number of joules. We also have another equation that relates the voltage to the electric field based on the distance between 2 points. In any uniform electric field, if we know some distance between 2 points, we can calculate the potential difference between those 2 points. And from this equation, you can see that if we rearranged for the electric field, we would have volts over meters. So 1 Newton per coulomb is actually the same as a volt per meter. If the potential difference is related to the electric field, and we know that point charges create electric fields around them, then there must be a potential around that point charge as well. So we'll use the letter V to indicate the potential, and I have this subscript saying that this equation is just for a point charge, and we can see that the greater the amount of charge, the greater the potential will be near that charge, and the closer that we are, the greater the potential will be. Kc, of course, is Coulomb's constant. So one way of visualizing the potential around a point charge is by using equipotential lines. These are like a contour map that tells you about the electrical landscape around a charged object or set of charged objects. These equipotential lines will indicate places around the charge that have equal electric potential, or they're at equal height for our electrical hill. This means that any other positive charge that was brought near this point charge Q would roll down the hill. It would be forced away. It would go down in potential right when we let go of that positive charge. So we'll look at equipotential lines for several different combinations of charges. This is what the equipotential line map would look like for a single positive point charge. So here, as we are farther away, the potential is lower, and as we are closer, the potential is higher, because R was in the denominator of the equation. So when we are very close, our potential is very high, something like 50 volts for this first line, and then the next one just a little bit farther out is 40 volts, and then maybe a little farther is 30 volts, and even farther is 20, and then 10, and when we're really far away, we can see that even a 5-volt difference is a very large distance away from that initial point charge that generated the potential. So you can see that it's like the potential is getting higher. It's almost as if our electrical hill is getting higher as well. And the electric potential is a scalar, actually, so it does add up to any other electric potential value generated by a different charge in the vicinity, but it does not have a direction. It doesn't point up, down, left, or right. So if you have multiple point charges, you would need to add up multiple values for each individual electric potential and see what your total electric potential is at some point in space. The electric potential can be negative, and that will mean that it is a negative point charge that's generating that potential. For example, if we have a dipole where we have a positive charge and a negative charge near each other, we would have high electric potential near the positive charge and low electric potential near the negative charge. This line right down the middle could be considered to be a line of zero potential. So it's like we're in positive potential over here. Our electrical hill is very tall or high, and we're at negative potential over here on the left. Our electric sinkhole is very deep and getting deeper as we get closer to the center of that negative charge. You'll also notice that the electric field lines in blue will always be perpendicular to the equipotential lines in green. So for a dipole with a positive and negative charge, here's a more precise picture. You can see that the positive charge over here on the left has a very large Voltage, 40 volts, 20 volts, 10, 5, 4, 3, 2, 1. Those are all positive. And then there's 0 right here in the middle. And then the potential values become negative. Negative 1, 2, 3, 4, 5, 10, 20, and 40 volts as we get closer to that negative charge on the right. So again, positive potential is like being very high up on an electrical hill, and negative potential is like being very low in an electrical sinkhole. For two like charges, two charges of the same sign, we would have 2 points in space that are symmetrical or equal in their electric potential. So here I have two negative charges near each other. The equipotential lines indicate that we have two sinkholes now and that they come together and create a unique shape for the contours of our electrical landscape. For example, here is two positive charges near each other, and you can see how the potential changes in this situation compared to the dipole in the previous situation. So here's a summary for all of your equations for a point charge. 2 point charges will feel an electric force. 1 point charge will generate an electric field. 2 point charges will have an electric energy between them. And 1 point charge will generate an electric potential. And here's a summary of the rules for your electric field lines and equipotential lines as well. That'll cover everything for Unit 9B. I'll see you in the next one.